Gases will be at 1 bar, solutions will be at 1 molar, and temperature will be at 298 Kelvin. True or false? A. Why is it false? Why is A false?
It's, well, for one, temperature is not included in standard thermodynamic conditions, which is implied by the little circle.
Okay. That's right. Did everybody catch that? It can't be A. A is false, so we could just eliminate that one. It's false because of the temperature. Temperature is not standard thermodynamic condition. We don't know what the temperature is. It doesn't specify it. In fact, having a delta G naught equal to 0 at 298 Kelvin is rare, because how often do we have K equal to 1 at 298 Kelvin? Rare, right? And you already, the reason I'm bringing up K is because you already have experience with a lot of K values. You've seen a lot of K values. And out of all those K values that you've seen, how many have you run across that are equal to 1? No, but we do delta G naught equal to 0 all the time. We set delta G naught equal to 0 because we want to figure out the temperature at which K will equal 1. But why do we want the temperature at which K equals 1? Because then it will be at equilibrium under standard conditions. And so this always throws people off for a loop, because they don't really get it, and they never really quite get it. And even my explanation doesn't really quite get it. But the explanation is this: you're under standard conditions, and there's got to be an equilibrium under standard conditions. So when do those conditions prevail? Well, those conditions are going to prevail at either temperatures that are impossible to reach. Sometimes you can never reach that. Sometimes you'll never get K, because the situation is this: just as we can change delta G with temperature, we can change K with temperature. And so we can try to tweak the temperature to get K equal to 1. When K equals 1, then B is correct. Gases will be at standard pressure and standard concentration, which is standard thermodynamic conditions. This is very weird, because here we're trying to tweak the temperature so that the K value is equal to 1. Why? Well, because we're under standard conditions. Standard conditions restricts that, and so that is to become at equilibrium under standard conditions. This is a restriction we have to have for standard conditions. And so B is correct. C is wrong. Or is C right? Well, C is right sometimes, right? Because when delta G naught is equal to 0, doesn't K equal 1? But not the temperature, because usually we have to tweak the temperature to get K, and sometimes you can tweak the temperature, but K will never equal 1, because the temperature is impossible to achieve. Sometimes when we do the temperature calculations, the temperature comes out to minus 500 Kelvin. Is it possible to go to minus 500 Kelvin? Or sometimes we go to minus 2,500 Kelvin. Not minus 2,000, plus 2,500 Kelvin. Is the temperature plus 2,500 Kelvin possible? Not for a lot of reactions. You'd end up vaporizing most of the stuff. And so sometimes, the temperature you do. And so how can we figure out how to tweak the temperature to get K equal to that? Well, it's actually pretty easy, because here there are two ways we could do it. We can do it from the standpoint of delta G naught. If we do it from the standpoint of delta G naught and try to figure out the temperature, then we just solve for the temperature at which delta G naught is equal to 0, and then therefore K is equal to 1. Okay, likewise, we want to do the same thing with K's. And so what I want you to do now is, I tried to derive an equation that shows the relationship between K and T, but it got screwed up. How did it get screwed up? Like, for example, this. This is the problem I want you to do next. so I didn't give it on this pad. I have to look at a folder again. Let me write it. Next week.
What day?
Thursday. So I'm gonna, this is it for chapter 19. This is the last part. Chapter 19. And so this is what we can do with this. And so, example, K and temperature. What we want to do is, sometimes what we want to do is we want to get a reaction to go at a certain percentage. And so let's say I just have some reaction, A plus B, this goes to G. Let's say we have AA, BB, and GG. And then what we want is, let's say I have some initial amounts of A here. Initial A, initial B, and let's say I have some initial G. And then I want to do this. I want to predict a temperature at which I'll get, let's say, 80% reaction. And so what I'll end up with is I'll end up with 20% left of A, initial. And so the question here is, at what temperature will the reaction stop at 80%? At what temperature will the reaction stop? So what I want to do is I want to figure out the temperature at which, you know, it stops here. Well, to figure out that temperature, what I have to do is I have to manipulate K. And so what I want to do is I want this. Let's say I just have, these are all 1 to 1 to 1. And so let's say I'm going to have 20% B initial, and then G over here I'm going to have 1.2 of G. Let's keep it simple. A is 1, B is 1, and G is 1 here. And let's say the concentrations are all equal at the beginning. And so this is what it would look like. And so stop here. To make the reaction stop here, I need to do this. I need to figure out what the K value would be here. So I need K equal this. It's got to equal 1.20 G initial products over reactant, 0.20 A initial, 0.20 B initial. And so if I can tweak the K, you know, if I can change the K value so that the K value ends up being this, then the reaction is going to proceed until it hits equilibrium. When it hits equilibrium, well, hey, that's what I want. I want it to stop here. And so what I'm doing is I'm targeting a certain ratio of product to reactant, which gives me a certain K value. And now I got to figure out how to get that K value, how to figure out at what temperature am I going to get this K value. And so what I want to do is this. I want you to come up with an equation to do that and tell me what additional information you're going to need to solve this equation.
What do you mean by stop at the 1.20?
I need it to stop here. I can't let it go on to 85%, 90%, 95%. I don't want it to continue on. I want it to stop here. In other words, I want the end of the reaction to be here at 80%. Is it possible to say, hey, reaction, stop reacting when you hit 80%? Is that possible? Sometimes it's possible if we can tweak the temperature. Sometimes it's impossible because the temperature, you know, remember, delta G naught depends on temperature. Delta G naught's related to K. K depends on temperature. So if we can tweak the temperature to tweak delta G naught, because then we could tweak the temperature to change the K. If we change the K value, we're telling where the reaction stops. Right? And so here, this is it. What we want to do is we want to figure out what temperature will the reaction just stop here and not proceed any farther. In other words, we need to set this as our final K value. Does that make sense? Somewhat? All right, so let's do a real problem here. I hope this scrolls down so we can do it. So I want you to do number 77. Oxides of nitrogen are produced in high temperature combustion processes. The essential reaction is N2 plus O2. So this is an unlikely reaction, but at high temperatures and high pressures, this reaction can be made to go. Nitrogen and oxygen will react to form NO gas. At what approximate temperature will an equal molar mixture of N2 and O2 be 1.0% converted to NO gas? And so what we want to do is we want to have just 1% of the nitrogen and oxygen be reacted to NO. And so that means what we want is we want the reaction to proceed. We don't want it less than 1%. We don't want it more than 1%. We want it just at 1% reaction. Is that something that's possible to do? Well, we're going to try it. We're going to try it by tweaking the temperature and seeing if that, well, the trick here is not necessarily delta G naught or delta G, because that's kind of tricky to do, but K gives us a way to do that, because if we convert this 1% over, then it's going to give us a certain ratio of reactants to products, and that's our target ratio, and that's what we're going to solve for. And so I tried to come up with an equation of how you can tweak K by changing temperature, but those equations weren't so successful, right? And so Celine came up with an equation, and so let's see, can you guys come up with an equation to figure out how to solve this? All right, give it a shot and see.